So I'm just going to take you on a tour of some of the scientific Python tools that are out there. This can be a little bit controversial, but I'm just going to go whole hog into showing you some of those things, and you can decide for yourself whether you think it's a good approach or not, and we can maybe get into some of that discussion a little bit more. So here's a rough outline of what I'm going to do. First, I'm going to give you a motivating example, and that's taken from my own work, which is a package called Proteus, which is the objectives are probably familiar to a lot of you, right? It's a science code. It's for solving PDEs in my particular area, and it happens to be written in Python. So it's kind of an example of what you might try to do in Python. And then I'll kind of go on a tour of some more standard things that have been used a lot in the scientific Python community. So a numerical array class called Numpy. The whole scientific Python community uses open repositories and version control a lot, and so I'll touch a little bit on GitHub, which is where a lot of the scientific Python tools reside. Also Bitbucket. Talk a little bit about self-documenting code and how that can be done in Python and using some additional tools in Python, one called Sphinx. Another one will be on regression testing. That's using the nose framework. A little bit about continuous performance monitoring. So obviously you want to do continuous integration where you're testing your code all the time and finding out if you've introduced bugs and things. But for us, who are interested in high performance computing, you might want to also monitor not just whether the test passed or failed, but what your performance is, so that you can try to kind of hammer on always sort of monotonically improving your performance. And that'll quickly touch on a tool called vBench. Then I'll talk a little bit about domain-specific languages. Aaron mentioned that this morning as being something that's kind of important. Going to a language that's particular for your problem and represents it in a nice abstract way can sometimes be a route towards better performance because the compilers can actually target that domain-specific language and try to produce optimal code because your language is rich enough to give it the information, give the compiler the information that it needs to do a good job. And then I'll talk a little bit about web notebooks, which is really more for communicating with your colleagues, making your great scientific tools available to other people in a relatively nice format. And then last, I'll finish up with scientific packaging, which is sort of what Aaron ended on, or at least the build problem. And I'll talk a little bit more about the distribution problem, which is important for everything. It's not a Python-specific thing. And I'll talk about the Hashdist tool there, which is something that we've developed in collaboration with several other groups. Okay, so first, sort of my motivate example, coastal hydraulic and hydrologic modeling. So this is the mission of my laboratory. We look at these problems in the civilian context, so dealing with storms and building infrastructure to protect people, and also in the military context where it's important to know about water depths and currents and things like that. And there are a huge number of challenges coming up in the coming decades. Demand for fresh water because of population growth. We continue to have large amounts of growth and development of our coastlines and islands. Of course, we've got climate change, and it's not clear what all is going to happen there. And then we've got sea level rise related to that, which we know is coming. And PDEs are a major part of this across all of those scales. And so just as an example, I'll show you a quick, this is a paper on water resources, just a subset of those coastal hydrologic and hydraulic models. It's a review paper from 2013. And you start going through looking at, chapter 2 on motivating applications. And we see immediately, okay, there's a linear heat equation. Equation 2 is a vection diffusion equation, a system of those equations. Go down, now we've got a nonlinear parabolic equation. Now we've got a system of nonlinear parabolic equations. There's a system of nonlinear parabolic equations with mixed type, hyperbolic, elliptic, parabolic, hyperbolic. And now we got a fourth order version of one of the earlier nonlinear equations. And it just goes on and on and on. Okay, these are very complicated PDEs. It takes a long time just to write them down in LaTeX. Okay, and now you've got to write codes that perform, you know, on HPC systems for these equations. And so you know, in this, you know, coming at it from this side of things, you know, we've got to get away from writing sort of single physics codes or codes that were developed to solve one equation, and then we said, well, it's kind of like these other couple of equations that we need, so let's tack on 3 or 4 more models onto that framework. We need something that's actually going to allow us to rapidly get these new formulations in, and at the same time rapidly apply new numerical algorithms to solving those, so new discretizations, new solvers, and things like that. So we've got to have a more modular process than the, you know, the big fat Fortran file that Aaron mentioned earlier that we used to be able to do to solve one of these equations. You know, you could write the whole discretization and the Krylov solver and the preconditioner and have it all together there. And that, you know, that makes life easy in some areas. But to respond to these challenges, we're going to have to go to something that's a you know, a larger framework and involves a lot more people working on it. So that's why we developed Proteus. Okay, so we wanted to you know, develop this type of a code that would allow us to attack new models and advanced methods. And we initially decided just to write a prototype, which is one of the reasons why we chose Python. Is we wanted a language that would allow us to make rapid progress in designing this thing and making it work. And then, of course, the way things work out, it went from being a prototype to being an actual R&D platform that we use for some production research. So we parallelized it using PETSI. Particularly now we use some nice wrappers called MPI for Pi and PETSI for Pi that I won't have a lot of time to go into, but they're very nice Python wrappers to MPI on the one hand and PETSI for solvers on the other. It contains at this point a lot of different 2D and 3D models, mostly for research and a few for a little bit you know, for application work. And it runs on a lot of supercomputers. Over the last probably, let's say 5 to 6 years, we've run it on, you know, all the generations of computers that have come through at the DoD HPC Center at the ERDIC, which have been mainly Crays, a couple of SGIs, and then also at the machines at the Texas Advanced Computing Center where some of our university collaborators reside. We've recently been working on the Blue Gene Q, but we don't have any results yet on that. And this has been a challenge, but I wouldn't say it's necessarily, you know, we've worked productively on those different machines. So here's a quick example. So say we want to solve this equation, which is advection diffusion reaction. So we've got an equation. In this case, we're going to make it all linear. So we've got our different terms or our coefficients in our PDE defined as, you know, some constant capital M times the solution variable U. The advective flux would be some vector B times the solution variable U. Our diffusion coefficient would be some constant tensor, and then we'd have a constant or a linear reaction term. So how would we get that into Proteus? Well, first we've got to define the equation. So we write, in this case, a class. Okay, so I'm sure most of you are familiar with object-oriented programming in C++, if not Python, but so Python supports this paradigm. We derive a class from a base class, which represents the coefficients of a PDE, and then we write some expressions for how to evaluate those equations. So it's not as nice as LaTeX or something that would be a natural symbolic language, but it's still relatively short. And it doesn't involve, the important fact is it doesn't involve the discretization in any way. This is the continuous form, or is one way to represent the continuous form of the PDE. So you can run that. All right, so next we continue to define the physics. We need to go from not just the equations, but we need a domain. We need to know the boundary conditions, the initial conditions, and I don't want to bore you with the line-by-line details, but right here, you can see we're creating a very simple domain. It's just a unit square, and we're giving it a very simple time interval from 0 to 1. And then we define the boundary conditions using a type of functional that's looping over our domain boundaries and returning functions depending on where we are on our boundary. And then, do some similar things for our initial conditions. Next, we define the numerics. Okay, so this is that important step to get a complete solver. We've got to now tack on some type of a discretization, some set of solvers. And I'll just point out a few things here. So, at some point we've got to say, how are we going to go from a continuous problem to a discrete problem? Well, we use the finite element method, and we choose a particular finite element space to approximate our solution variable. We're going to use quadrature, so we give it some quadrature rules. And then somewhere down here at the bottom, you should see that I'm also once I've turned my equation from a continuous PDE to a fully discrete PDE, I've got a linear algebra problem to solve, and I've got to pick a matrix format and a solver. So in this case, I'm going to use a sparse matrix, and I'm going to use PETSI to solve it using a Krylov method. And then in this particular case, I'm using some default options for PETSI. If I were running on a supercomputer, I would use PETSI's ability on the command line to further specify that Krylov solver, although you could also do it in the script if you wanted to. So then last step is to solve this and plot it. Again, not going to go through all that line by line, but we generated a triangular mesh. We ran this function calculate solution, which calculated the solution over the time interval. We checked that it didn't fail, and then we plotted it. So, this is a baby example, but this is the idea, is to do this with things that aren't, toy equations. So I won't take you through that for this problem, but I'll show you just kind of a fun example of something that we did do. So this is a laboratory experiment that we solved with Proteus's multi-phase air-water code. And so this one, this particular data set we did generate on a Cray, our Cray at the DSRC. And it was probably not a huge, maybe 1,000 processors, 1,000 to 2,000 cores that we ran that on. So this is kind of at the lower end of the things that we really want to be addressing with that 3D code. This would be considered a validation problem, not a field scale problem. But a step forward in HPC was fundamental in getting that result. So again, we're doing, and this is using the Python framework. This is mainly just to show you that it's gone beyond a prototype at this point. So that's the motivating example. We've done some things. We've liked this Python approach, but we've primarily built on top of a lot of really good stuff that we've gotten from the wider Python community, and that's what I really want to focus on today. All the different open source packages that we depend on, and also some of the practices that we've copied from our colleagues who have taught us a lot of important things about software engineering just by looking at what they're doing. So first, I'll talk about Numpy. It's the de facto standard for the numerical array type. Okay, so I'm sure you're all familiar. In Fortran, you've got a standard array that you use in Fortran for multidimensional arrays. In C++, there was a long time when there was no standard array. There's val array now and some standards, but people were doing heavy stuff in C++ long before there was any standard. Same thing in Python. Unfortunately, when they designed the language, they didn't build a numerical array as part of the standard library, and so Numpy became that. Is it going to become part of the standard, Aaron?
There's a thing called a buffer interface that's now in Python, which implements 80% of what Numpy does, which is basically generic multidimensional array processing. But no, I don't think it'll ever be a native type.
Okay. So that's one of my pet peeves. If I had it all to do over again, and when I look at a language, if I'm going to be doing what I do, I want to see that the language designer built into it a numerical array from scratch. It's always irritated me about C++ as well. But this works very well, and so it's a de facto standard and allows you to drop into highly optimized standard libraries like LPACK, BLAS, C. When we drop into PETC, we're doing that using the Numpy array to provide PETC with direct access to packed, packed array structures. So here's an example of something that you could do with Numpy. So I'm at a Python input cell here. I'm going to import Numpy. That's pulling in that module in. I create some vectors, x, y, and z, which, that's fine. I can multiply the vectors x by 2 and return a new one into y. I can add vectors. You can also do things like stack vectors together to produce other things. So in this case, I did it to produce a matrix. So, just simple linear algebra. Again, you've got access to a lot of libraries below there, so you can do things like compute the eigenvalues. Of course, I was kind of bad then, and I created a matrix that's got some 0 eigenvalues. So I need to fix that if I want to do some linear algebra. So I do something that's very nice in Numpy. It's called slicing. Okay, so you have a nice indexing functionality for these matrices or arrays in general. And in this case, I'm going to grab the first row, and I'm going to just zero out from the 0th element to the first element, okay, which is just one element, right? So the syntax here is sort of, you can think of it as from the beginning to one past the end. Now for the second row, I'm going to zero out from 0 to 2, third 0 to 3, so I'm making it upper triangular. It's got non-zero diagonals to get rid of those 0 eigenvalues. And then I can solve a linear algebra problem, okay? And then, so I've solved my system AX equals Y, and then I've checked the error there. So there's a huge amount that you can do with Numpy, and I don't have time to go into it, but hopefully this gives you a flavor for the ease with which you can do linear algebra and lots of other array-based computing with Numpy and Python. So some other resources I mentioned earlier. Of course, the linear algebra that I just showed you is not at the level that most of us care about. You might be doing that on each core, but you really need to be doing parallel linear algebra. And again, MPI for Pi and PETC for Pi. In some ways, for me, they're de facto standards now for working with MPI and for working with PETC. They're very high quality wrappers developed. The lead author is Lisandro Dawson, and he works very closely with the PETC developers. I use them a lot, and I've learned a lot from the kind of things that Lisandro has done. Okay, next would be putting version control into practice. Okay, so I know that you guys have had some talks on how to use version control, and some of you may be already using it a lot. But you might be also wondering how should you get started. One of the things that it's going to require, again, as soon as you go beyond one person, if you have a team of 2 or 3 or hopefully more than that, you've got to have servers that you can all hit while you're traveling and when you work at different organizations. And so you've got to set up repository hosting. And we struggled for many years within our organization, trying to get support for, nice kind of organizational repository hosting that would allow us to work with our university collaborators. And at the end of the day, we're scientists, and it's hard to keep justifying those expenses. So nowadays we've pretty much switched to GitHub. We do a little bit on Bitbucket. So we have an organizational account set up on GitHub, and all of our projects are managed on there. So that, just as an example, because I know where things are, you can look at the Proteus repository. It's got links to the static documentation. It has an issue tracker that we use to help us stay on top of things and also to plan out our development. It's got a wiki where we can kind of on the fly produce instructions like how to build on the Cray or the SGI or something like that. And so I find that this is it's a definitely worth considering going ahead and using these public services rather than trying to roll your own inside. They also add easy hooks for continuous integration. I'm not going to have time to talk about it, but there's a great tool called Travis, and it's pretty easy to hook in your version control, your repository, so that when when somebody pushes a new commit to your repository on GitHub, it immediately kicks off your regression testing suite, which is nice and important. So now moving on. So moving on from repository hosting, hit another important thing, which is documentation. And I just have to admit right off the bat that it's just hard, and I don't do a good job of it. So I'm going to suggest some tools that we've used and we've seen used effectively, but I have not used them well myself. But one of the important things that I do believe is that if you're going to put the effort into it, then you shouldn't have to put the effort in again. Okay, so I do believe in using inline documentation. So Python has the notion of a document string, which I'll show you in just a second. So it's part of the language that you can include documentation as part of the definition of your function, and then it's got help systems built on top of that. But of course, even in other languages like C++, you can use a tool like Doxygen, where you give it a special comment, an extra flag within the comment that'll say this is part of the documentation. You can build very nice documentation for C++ codes with that. My point there in that you should have something to show for your effort is that, number one, you could choose to have something that's easy to keep up to date if you went to the effort of putting it in there in the first place, and you should have something that generates nice documentation formats for your users, so web formats, PDFs, and things like that. And that's what these tools like Sphinx and Doxygen allow you to do. So I might be able to show you an example of the output of Doxygen the way that we use it, but I'm going to hit the Sphinx part first. So again, we're at a Python prompt. We're writing a function foo that takes A and B and it adds them. This triple quote here, this just tells it that it's triple quoted and the R is for raw, so that it knows not to interpret some of the special characters, just produce an ASCII string from this. And Python knows that because this string is preceding the definition of my function, this is the doc string for this function. And I'll show you how that works within Python in just a second. But the additional things here are that I've used some syntax here, which is called restructured text. So it is text, but it's flagging some things that will allow the tool Sphinx to later come along and produce a nice documentation page from this. And you can also do things like hide to-do statements that will be collected in your web documentation so that you don't lose track of the things that you told yourself you were going to do before the end of the year or whatever. So this is what Python would do with that string. Now I can call help on the function foo, and it gives me back that string. It doesn't do anything with the restructured text, but the main thing I want to be getting at here would be just that first line. What does it do? And if I wanted to get into more detail, I might go somewhere else. Now, I'm using the IPython notebook, which I'll talk later, and it has gone and added some additional stuff on top of the regular Python help system, and it gives you this question mark syntax, and that gives you a little pop-up down at the bottom that gives you a little bit more information than just the doc string, which is a convenient sort of add-on that they have created as part of the IPython notebook. So what are some examples? This is a site that is built entirely with Sphinx. So they took their Python package called matplotlib, which is another package I won't have time to go into, but it's a great package for plotting. And they built it up using using those inline documentation strings and also the Sphinx documentation generator to run on their package. And so the things that I was just showing you earlier about, let's see something that would be interesting. So these are those, this is documentation generated from those doc strings with the additional annotations in restructured text, so that Sphinx can do things like create lists inside there that are nicely formatted, provide links between, like in this case, the current class and the base class. You can also build up a lot of documentation on top of your source code just in a separate text text file. In this case, they've got a gallery, which is particularly useful for plotting because a lot of times, we're in a hurry. We're trying to write up our presentation or write our paper, and you just want to say, I really think it would look good if I could plot something to look kind of like streamlines and errors. So you go to their gallery and you find what you're looking for, and then you get a full demonstration of that and how to actually do it. And you cut and paste that code into your code and modify it to do what you want to do. So that's a great example to look at. The Proteus example, again, it's just an example that I'm picking because I know where things are. In this case, we have a bit of a mess right now with our build bots, but we've made a home page with various important things like references to papers and that sort of thing. We've got that inline documentation coming from the doc strings. And you can see here that we're doing things like using LaTeX inside the doc string, and then Sphinx is processing that into the equation. In this case, it's a module of analytical solutions, and so it's nice to be able to see what is it the exact solution of in a nicely formatted equation. So you can do math in your doc strings. I will try to see if the Doxygen documentation, one of the downsides of, oh, it's there. Hey, all right. Again, one of the downsides to automatically generating your documentations is sometimes you screw it up and you don't realize that your web server is no longer displaying the important thing. But in this case, it magically is. So I've got Python. Proteus is designed at the high level in Python, but it has whole class hierarchies in C++ down below for efficiency. And in this case, we use the Doxygen documentation when we drop down to the C level. Aaron was pointing out that you can now use Sphinx to document C++ code as well. So the Sphinx is this tool very similar to Doxygen. It's going to look at your source code and try to extract the documentation out of it and produce a nice format, in this case a web-based format. When we were looking at how to do this, I don't remember all of the reasons for doing it, but I decided to just stick with using Doxygen in C++ because that's how I was familiar with documenting my C++. And so we kind of do this hybrid of using Sphinx and Doxygen to generate it. So now moving along to testing, it's critical. And again, this is one of those ways where my motivating example of Proteus has again exposed my failures in this area. It's very hard to keep things up to date and to find the time to actually write tests at the level of granularity that is really useful for keeping your code working. We tend to get focused on driving to this larger problem that we need to get that result, and we need to be able to show that it works, and that's really too coarsely grained, to really test the code the way you need to. And so we failed in that way a lot, but the nose module in Python actually makes it quite easy to write these very fine scale tests called unit tests and to automate the testing of those or the running of those tests and the nice output. So here's the nose website. I'm going to drop back and just show you an example. So in this case, all I've done here is written a test. So from my earlier thing that I wrote, they just added two numbers together, and now I've appended test underscore onto that, and I've grabbed some a tool from the nose program called EQ. And so what this would do is it would say, okay, when I call foo on 1, 3, is that equal to 4? Okay, and the nose package provides a fair number of these kind of special purpose assertions that are useful for writing tests. I don't, so skipping on to when you would actually call that on your code. So we have a directory in Proteus called test, and inside that it has a number of modules, and those are filled with some test functions, okay? And this says test underscore, and then it does something. And a lot of those tests don't do anything more than call one of those functions from nose to do an assertion. Some of them just call assertions. But the nice thing that nose gives you is the automated discovery of these tests that are inside your source code, and it calls them and runs them in a nice way so that you can see what's failing and what's not. So it looks like I've got a failure in the little L2 norm or average, and I've got some other failure. So I just ran this on master last night and hadn't figured out where those have crept up. But that's the idea. So much like with the documentation systems that we talked about earlier, now you can start to kind of integrate your testing with your source code. If you want to just stick test underscore foo1, foo2, foo3 at the bottom of your modules, you can do that, and Nose will just find those and run them, okay? And again, you can use a hook script in your version control to just do this every time there's a new commit. You can get much more complicated than that, and I find that when you start writing tests, you often, at first you think, well, I can just call something and then I can just assert something and that's good enough. If that blows up, then I'll catch it. But to do things well, again, you start to realize, well, I actually need a function that doesn't really test equality. It might test equality up to round off. And then you start to realize, well, to test this one little segment of the code, I've still got to do a lot of setup. And when I'm done with that, I've got to tear down a bunch of stuff. And so you start building these tools that you need to actually write good tests. And you may not have time to do that. And a tool like Nose has done a lot of that thinking for you and has done a lot of that hard work for you at building up a testing framework. And so again, this is one of the things that's been nice about using Python is there's been this larger community that we could tap into that cares about a lot of the same issues that we do, and maybe is a little bit more advanced in certain areas because they might not be so driven by some of the internal scientific or organizational constraints that we are. Question?
So how do you develop unit tests for functions that require horrendously complex inputs or take like an hour to run before you can actually get to that code? This is a problem I constantly have.
It's true, but that's actually was my point from earlier. Sometimes to test something really small, you've still got to do all of this very complicated setup. These things are called fixtures in the sort of testing side of things, and Nose has support for writing those fixtures. And so, again, you want to write your tests to be small, but your testing module can reasonably become a pretty complicated beast, and Nose kind of helps you to organize some of that fixture code in a nice way. I don't know, Aaron, you've got more experience with it than I do.
Two comments. So the first is that Nose on its own is not great for a lot of linear algebra or array-based stuff that you need to do, and so you should use Numpy testing, right? And there are examples of using Numpy testing in SciPy lectures, which are online, and that'll do things like measure to round off error, compare two arrays, right? You don't have to. You can compare two three-dimensional arrays or two one-dimensional arrays. It'll take care of that for whatever tolerances, relative or absolute, that you want. But coming back to the other problem of currently the only way I know the code runs correctly is if I take it on 1,000 processors, run it for 24 hours, and the exact result, which is some giant array, is the same array that I saw 6 months ago. If you're in that situation, you haven't broken down the components of your program enough to understand how the different pieces are interacting. And so if you have a linear algebra module, like there, that is just testing basic linear algebra, right? Or if you have another really classic example is finite element assembly, right? So small pieces, like just assembling one element, what goes into that? Maybe there are different boundary conditions that you need to be able to check that all of those things are happening, all before you even get to one large matrix. So there are two things. Break it down into smaller components and also solve smaller problems. So instead of solving the big, highly resolved problem, solve maybe even a small piece of it or several small pieces of it. The whole point of a unit test is it doesn't solve everything. It just solves a small piece and makes sure that that component is working correctly. And I agree, it's not easy.
And one more practical comment on that would be that you can, to get, or pragmatic, right? You got to start somewhere, and if that's your test, then you can do things like use your, like we use build bots with Proteus, and you can schedule those to run those big tests less frequently, so at least you're hitting that test in an automated way once a week or once a month or something like that, and that's, that may be the best you can do, and that's a little bit higher level where you're kind of just organizing it, and maybe you've got a big underscore tests directory, and you just hide that from nose for your routine testing. Okay, any more questions on testing? All right. Yep.
Does anybody actually do automated testing on supercomputers? Like it's actually setting up to run JavaScript and things like that? And how, if so, did they mention, do you have any numbers for how many hours they're burning doing this?
I don't have any. So we at various times have run our build bots on machines at our lab and at Texas. And we did not run, I wouldn't say that we were running a lot of hours, but we kind of came up to this question and began discussing it with the system admins and things like that. And for me, it's still an unresolved issue. I think it's important for us to all say that, I need automated regression testing, and I need it running on the supercomputers. It's not enough to have this great system that runs on my workstation in my office because it just doesn't discover some of the errors that we're going to see on the HPC systems. And so the way that I was doing it was I had set up these build bots as me using my allocation, and for whatever reason, that was okay with the policies at the particular time, right? You can't run cron jobs on there and things like that, the little more old school ways of doing things like that. But the way these build bot works, because the way they went out and hit the build master was okay with the security model. But it was really kind of, again, it was the first time that we did it. We did it on a couple of machines. We haven't used it extensively. We would like to, but that's my experience with it. And
I'll add that we don't have sort of a separate allocation program or anything like that for just validation. But different projects on the leadership facilities do targeted regression testing within their allocations. And not everybody, it's not a requirement, but it would be nice if it could be, but it is not a requirement. And those though tend to be targeting not like full system runs. So they could absolutely do that if they wanted to, but they tend to target mid-range to small-range tests to make sure that the functionality is there. This is very valuable, particularly on systems that that are sort of more bleeding edge. Total time, it's a small number of projects that do that now. To do this now like on the facility hardware, I say that I could only list off the top of my head 4. and they are burning a small fraction of their time, right? You know, they're trying not to burn their allocation doing this. They don't do it daily. But that's sort of reasonable when you consider the speed of change of the code sometimes that they're using. I mean, because the regression testing can also be a function of how fast you're developing. So they're not necessarily testing every day because they're not even developing on every day. So I didn't totally answer, but that's approximate.
Can I just add a comment? I mean, we do all of this, and we have regression testers and everything. And the biggest problem for us, though, is that we always have bugs which only come in at very, well, relatively large core counts. And sometimes even getting that bug down to a small core count means that we just have a bug on 30,000 cores instead of 300,000 cores. And that's a huge, huge problem that I don't think any of us knows how to answer, because the debuggers don't work at those scales. We brought down Mirror a few times, got our wrist slapped because of that. You know, just trying to do what, get our codes to work, and it's a huge challenge. Even, but you know, of course, everything you've talked about makes perfect sense, and you have to do all of this, but it only gets you a fraction of the way where you want to be, really.
Yeah, I mean, I can add to that. We had a bug in our program where we were running out of MPI communicators, and that only shows up when you go, you know, almost to the entire machine of Myra. And if I was going to take the first speaker's advice and turn that into a regression test, you know, it's tough to get that time to actually make sure that still works.
Well, there's a difference between a bug, whether it be the bug that you own or you find in the software stack or what have you, right? And what you necessarily really want to make sure to always have a unit testing for, right? Ideally, right, I think a unit test should suss out everything, but there are times where it's harder to do that. And one of those tends to be when you're touching the system software. So I don't know if this was because we've had that exact kind of bug in the system software stack, right? Hopefully that's something that the system software stack is capturing. That's
I'm the first speaker, and I actually would like to clarify that. So if you run into an error where your MPI implementation is running out of communicators, first of all, the unit testing that should have caught that is not in your library. It's in the MPI implementation, which should very much have a test to create the number of communicators that you're supposed to be, that you're trying to create, or an assertion that fails out hard and says you're trying to create too many communicators. So this is actually, right, part of this general problem where you can be running on libraries which are battle hardened and very good, but still have a corner case. And you are going to be hitting those corner cases in supercomputing all the time. And the more you do to protect yourself in your application code, the better a chance you will find or be able to isolate that library failure. And what's going to happen is that you may start with a relatively low quality code when you first start writing your code, but you will rapidly need to get to a high quality code if you are going to develop effectively on large scale machines, because you will run into these bugs. They won't even necessarily be your bug, but you will still need to go be responsible for finding that and fixing it. Is that a fair sort of, okay, great.
Question?
I was just going to make a comment about testing that particular bug. I think the right strategy for we ran out of MPI communicators. That was the problem in the software stack that wrote our application. The way to turn that into a test case is not to run full scale and provoke the actual problem, but to recognize that we ran out of MPI communicators. So make a test that allocates more communicators than you think you need, check that it works. That you can do within your allocation in a fraction of the time. So we had a bug once on blue gene L, where if you passed in a null pointer of length 0 to MPI bidcast, the system software crapped out because it dereferenced the null pointer, even though you weren't actually sending any data. So you can well write your application to do a sensible thing, expecting it not to work. So this can be tested very easily. What you don't want to do is provoke the whole application.
Yeah, again, I was going to kind of address it obliquely. The case that where we were doing this, what our build slaves were doing on these machines is they were building our whole stack, which included PETSI, our own custom builds of PETSI and things like that. Numpy, the tools that I was just mentioning, and we were running their regression tests as well. And we were usually running them on 1 to 2 nodes, which on our machine was 16 to 32 cores. And so what we were doing, so 2 things. That's one, a more concrete example of the size of the thing that we were using on our application. So nightly using up an hour of time on 2 nodes was not that big of a deal. But I think the other important thing is that we were testing our whole stack, not just our code. And sometimes that, you'll have a test for allocating a bunch of MPI cores in MPI for Pi, our wrapper of MPI, and that'll catch it. So just, I think testing the hell out of it at fine grains across your whole stack also helps you discover those really hard bugs that they only seem to show up in this really complicated example. But in this case, it has nothing to do with your really complicated example, except in that one case where you're, again, once you figured it out, you could allocate it. But I mean, you could identify it and reduce down to it. But if you have a really thorough testing framework that's hitting your whole stack, then that can help you discover it as well. And I tried to pull up an example, but I've since kind of redesigned some of these things so it's not testing some of those dependencies in our stack.
How many times do you find yourself refactoring all these tests? How often?
Not as often as I'd like to. Unfortunately, to be honest, these tests got written because we had a developers workshop, with some of our scientific and mathematical collaborators, and we were developing these tests as an example of how to develop tests, and that's when we really allocated time to actually do it. We really need to set aside, I need to set aside a little bit of time every week, I think, to write a new test and to check coverage, and actually show you a tool in just a second that talks about coverage, which can help pressure you and your developers into trying to move forward on getting more testing. But of course, the other thing is, again, the organizational support for testing. We like to say, not to show your managers what you've done, because as soon as you show them that picture, they say it's done. We don't have to fund this anymore, right? And that's the thing with these tests is it's like, it's such an iterative design and development process that somehow we've got to get that message across that it's not over when you see the pretty picture. That's when the regression testing gets even more important, that you get it really fine-grained and you get your 100% coverage so that from now to eternity you can continue to get that result. But at least I haven't always made that, haven't factored that into my proposals and the timeline and the time spent as well as I should. Does anybody, Aaron, do you have a better idea on the fraction of time that you should, or the frequency that you should refactor your tests?
So the ideal, highly mature, so there's 2 levels of code here that are very common. They're the library developers who are writing code that's used by, say, hundreds or thousands of people. And then there are applications codes which may be used by 5 or 10 people. But if an application code generates a high-profile result, say it goes into Science or Nature or some other high-level result, that result will be reused potentially by thousands of people. So even though that application code itself may not be used by many people, the result is as important as a library which is using thousands of code, and then it needs to be at that same level of maturity. So when we talk about maturity, code coverage starts covering, say, 80 to 90% of your code is executed, or all of these small pieces of your code are executed, and you'll actually know when it's time to write new tests or refactor tests when 2 situations occur. The first is when you find a bug, and as we mentioned it earlier, if you find a bug, then there was a test that was not being captured or not capturing that bug, right? If somebody manually reports to you that a result is wrong, then you had a test that wasn't capturing that. That's the first. The second is when you add new functionality to your code. When you add new functionality to your code, it should be accompanied by a test that validates that functionality. And that way, in the future, if that functionality gets modified, changed, or broken, the test will pick that up. So those are the 2 times to really be concerned. Of course, if you're starting with a code that doesn't have any tests, then the first thing to add is that big validation test, like the first thing that just reruns all the code and comes out with the same result. And then after you've got that, you can start breaking that down into these smaller unit tests, which are easier to run. For example, Numpy has a suite of, I think, over 1,000 tests that run in about 1 or 2 seconds that quickly exercise almost the entire stack in a variety of ways. And that's kind of a very useful thing to have. But again, at the very peak of maturity, you're at that stage where you have this well-developed unit test library. And not everybody is going to be there now, and not everybody is going to be able to get there sort of with their project. But if you are aiming for that high-profile result, or you are running on a very big supercomputer, you will need to get there.
And I'll say another, just to put in one more plug for nose. I mean, I think most scientists, most of you in this room, when you develop your code, you are developing it with tests. You just might not be thinking of unit testing and kind of having these automated tests run. And that's one of the nice things about nose is there's very little hurdle to get over to go from writing something that just runs your code and make sure that it works, which is the kind of test that most of us write as we're developing our code, to things that nose will automatically pick up and run as regression tests. And I'm not saying that's enough, but I think it's important that we admit that we don't have a lot of time to work on this and don't have a lot of support for doing it. And so a tool like Nose that will allow you to just take all that code that you wrote as you were developing your module to check that it was working and turn it into unit tests that can be run in a nice automated way. So there's very little additional stuff that you need to do to, besides test underscore, turning them into functions that can be called like that. Okay, so I'll come back to the coverage issue that Aaron mentioned, and that this comes into this question of how often do you refactor. But real quick, I'll talk about a neat tool that looks at continuous integration plus performance. So again, if you have this glorious code that has all these unit tests that run and check your code at a nice fine level, that's great. But we care about performance, and so in a sense, it's an error for us or regression when we did something that makes our code run 5 times slower. Okay, we need to catch that just as well as we need to catch incorrect code. And you could do that with something like Nose, but again, in the scientific Python community, somebody has taken this idea and they've wrapped a little bit more around it and built some nice tools that you can just piggyback on. And one of those is called vbench. And so basically the idea is that when these tests run, you can have it'll plot nice graphs that show the performance over time of your performance test, and so you can catch significant increases in time that get committed to your repository. See if there's a better benchmark to look at.
Is there any tool out there to tell you how much of your code is actually tested?
Yep, that's my next item. So this would be the idea of coverage. Okay, so there are various automated tools for checking your test coverage. I'm just going to show you. So one of the SciPy, or one of the scientific Python community tools, is this package called scikit image, which is for image processing. And they've incorporated some nice coverage tools into their their build system, their automated build system. And so it gives you this nice web page that gives you some overall statistics about how much of the actual source code is tested, and then it gives you sort of file by file, what's your percentage of tested code, and this is sorted from lowest to highest. So we're starting off with stuff that's not tested at all currently, and these would be, like Aaron was saying, potentially things that it's new code that got committed. You want to catch that right away. We've written new code and we haven't written any tests for it, so let's get on that. To code that's more heavily tested. And again, you can track this, when a new commit comes in, you can see the changes, and that helps, put pressure on yourself to do a better job with writing tests to get coverage. And I don't actually know actually know how they're doing this. Aaron, do you have a comment about the tool they use to build?
Using or familiar with Travis CI. Okay, or BuildBot or another continuous integration server. So it piggybacks off of the continuous integration server. And it's another free service that actually just runs on top of GitHub. All you have to do is activate it. And it will look at your test output. So there's this sort of XUnit output, which tells you what the coverage statistics on the tests were for each of your files. And then it just processes that into a nice running graph and running summary. So go ahead.
Bitbucket. She asked if there's something similar for Bitbucket.
Yeah, a lot of these external tools they're external, right? They're not GitHub projects, and so they can hook into any sort of online repository that exposes what's called sort of this commit hook, where basically there's a web page or a thing that gets modified when the file changes. It can also sometimes do a push too.
Is there something for C++, C or C++ as well?
These will be independent of Python. I should have mentioned that ahead of time. This is really associated with the version control system. So again, the idea is when you have a commit that hits the repository, it's able to trigger other processes that are external to it. So in the one case, you get a new commit, that triggers a testing framework. It could be nodes, it could be just your script that runs a bunch of tests. And in this case, it can trigger, a coverage test. So people use these hook scripts to generate even style checking, to say this doesn't match our, style of C++, or this is how much code doesn't match the style. So there are lots of neat things you can do there, to help your project produce higher code somewhat painlessly.
Yep, automated testing, automated code coverage analysis, and then the final thing is automated documentation generation. So there's a website called Read the Docs, which actually automatically parses a formatted Sphinx file, and it will generate your documentation for you based on a new commit. So you can create a new branch or a new pull request, and it will update a web page with that documentation.
That's there's a separate link on the Proteus website that is exactly that. So when our BuildBot runs nightly, there's a special one that runs, and it goes, in addition to building the whole stack and running some tests, it runs Sphinx and Oxygen to generate the documentation. So there's a developer's link that'll show you exactly what the auto-generated documentation looks like based on last night's commit. And I believe PETC uses a similar tool. So a lot of times on these packages, you'll find a kind of your static documentation that corresponds to a release, and then a nightly developer documentation. And those are, again, just triggered by something that is watching the repository or something that the repository triggers. Okay. So moving on, this is kind of now going off of the lower level software engineering and the different kind of tools that you can use to help produce better software, to some more scientific considerations about how you actually write your code. And this ties in a little bit to the discussion we had earlier about why use a higher level language, why use in this case, a domain specific language. And coincidentally, it also relates back to our dinner talk last night, which is, how do you write code that can survive the evolution of these architectures? When you need to get top performance out of the machine, you end up having to write a lot of low-level code that does a lot of things that may not work in the future or on different machines. Okay, up in the front earlier, we were talking about inlining. You might have a machine where you just need to inline a bunch of stuff, to make it run fast. You might have, times where you need to unroll loops in different ways. For most algorithms, there's a memory computation trade-off where you can pre-compute something, and in an ideal world, you're saving operations, but in the real world, pre-computing uses more memory, it accesses more memory, so it's actually slower. So you write faster code by taking all of your computations and sticking them into a single file, and not kind of modular or pre-computing things and you know, doing things that would look kind of stupid on paper, but that's what makes it run fast. Okay, so this is, you know, well known that this occurs, and one way to potentially get out of that is to build kind of a compiler pathway. So you can write your algorithms in a language that is tailored to the type of thing that you're writing. In this case, I'm going to talk about finite element methods. And so you can specify your finite element method in this mini language. And then what the code actually does, and this is particularly easy to do in Python because of the you know, it's not a compiled language, so you can write code that writes code and calls itself, okay? And so in this case, you can write high-level code in a domain-specific language that is then effectively compiled into a much more highly optimized bit of code that is imported and run. And so that step of going from the domain-specific language to something that is compiled can be very much tailored to the type of algorithm that you're writing. And that allows, in the long term, to have multiple back-ends to that algorithm. And so you're in the case, instead of hand writing this highly tuned code, you might hand write the first generation of it, but then at some point it becomes a kind of template that you generate. And so let me show you that real quick with a Phoenix example. So Phoenix is a hybrid Python C++ code with a lot of the same goals as Proteus, and they do a lot of really neat things with the DSL. In their case, it's a domain-specific language for the discrete weak formulation of the PDE. Okay, so you take your PDE, you do something to it, integrate by parts, turn it into a weak formulation, and then you choose finite dimensional subspaces of your, you know, your Sobolev spaces or whatnot to build the discrete, the fully discrete version. What Phoenix does is it has a special language for that fully discrete version. And I'll show you what that looks like. So in this case, of course, we have to solve the Poisson equation as an example. So we're going to solve the Poisson equation. They do some math up here in their documentation to generate the variational formulation or the weak formulation. And now we get down to the implementation. Okay, so again, this is Python, but it is actually a domain-specific language that's embedded in Python. And so you can see building up a trial function, a test function space, the coefficients of your PDE by declaring, you know, this one's going to be constant. And then we build up a bilinear form by saying, okay, I want to take the inner product with this guy. And that's my trial function. This is my test function. And then I'm going to hit that with, I'm going to integrate it some, multiplying by a dx to represent the integration. I can also specify the linear operator corresponding to that bilinear form. And then I put that together and I solve it. So this is complete code for solving the Poisson equation, but it's doing this kind of neat trick of writing it as an expression and then generating from that expression highly optimal code, you know, based on a lower level C++ set of sort of C++ macros or shoot, I can't remember the name of it now, but it's a lower level set of kernels that this generates. And so this is, again, grabbing onto this at a fairly abstract level, but in a very constrained sense. We're only dealing with a mini language for discrete weak forms, allows you to do optimizations on the back end. And I'm not familiar with all the recent work, but there are various groups looking at special compilation of these weak forms to get you know, optimal performance out of your two major steps in a finite element algorithm, the assembly of the residual and the assembly of the Jacobian. And they can do other neat things because they have a hold of this expression at a high level, like automatically generate the adjoint or the discrete approximation to the adjoint. So you can do things like, adjoint-based uncertainty quantification and things like that. So that's an example. And then another example, and this is closer to what we're trying to do with Proteus, and we're working with Andreas Klockner at University of Illinois. It using the same approach, using it, building an embedded domain-specific language, but in our case, targeting the continuous form of the PDE. And this would allow us to target both finite element backends and finite volume backends, and is a little bit more appropriate for our types of users. So we're looking at other engineers and scientists who are working on new PDEs, but who are not experts in the discretization methods. And the problems themselves, the physics are complicated enough that we feel like having a domain-specific language that allows you to write these complicated PDEs in a language that we can then kind of manipulate so that we can manipulate the expressions is a good way forward. And that's compatible actually with Phoenix. It would just be kind of a two-step process where you generate the high-level expression for your continuous PDE, and then you basically generate the discrete weak form language in Phoenix, and then below that you generate your fully discrete optimized code. Question?
So just to make sure that I understand correctly, so basically in these PDEs you might have different operators, right? Some of them might be hyperbolic, some of them might be parabolic, and so on. So you're saying that just giving the PDE at the top level, then you can take that one and get the highly optimized code that can run as fast as one that is considering the equation at the discrete level and is trying to squeeze the performance out of it? That's
the goal. And with Phoenix, they've done some demonstrations of that at a slightly lower level, where in their case, you've already chosen the particular weak formulation that you want to apply those manipulations, and you've chosen the finite element spaces, whether you're using quadrature or using analytical integration. So they make those are represented directly in their domain-specific language, and then going from that step to actual code in a way that is competitive with hand-rolled finite elements has been demonstrated. And where where we would like to go would be one step higher than that, where we can go from a nice representation, of the PDE, like you pulled it out of that paper that I showed earlier, and then provide a pathway to several different numerical methods, finite volume methods for conservation law, a discontinuous Galerkin method, and then from there down generate optimized code. Again, to kind of help prevent this stovepiping of entire pieces of code over a particular equation in a particular method that we tend to do these days, or have tended to do over the last couple of decades. All right, any more questions? Did that answer that, sort of?
Yeah, to some extent. How hard or easy is to actually solve different equations in different parts of the domain or something?
I have, in Phoenix, I've seen some examples of that sort of multi-physics problem. A lot of those issues, and I haven't really talked about this at all, but for solving these kinds of problems, there are all these computational geometry and mesh generation problems that end up becoming the barrier to the solution there. So the fact that you use a DSL or you hand roll it or whatever is not really the stopping point for a lot of those types of problems. It's that we lack or we do not have available some nicer mesh generation and computational geometry tools that allow you to do that. And so the person that was working on this in Phoenix spent a lot of time using a European graphics package called Seagal that does a lot of really nice manipulation, but it's really from outside of our community. It's more from the computer graphics and sort of gaming side of things, where they have more sophisticated implementations of manipulating these discrete geometric structures. And actually, that reminds me of something that I wanted to point out, because it looks like we'll have enough time to finish up. We were chatting during the break about using Python in these in the supercomputing setting. There's some real issues. You're dealing with shared libraries. You're dealing with an interpreted language, so you have not necessarily access to the types of optimizations that you have. But the approach we used in Proteus, which is kind of 2 levels, really we haven't seen the performance hits due to our use of Python. Where we've gotten hit is on things like our mesh partitioning or our mesh generation and the way we load things in, which really has nothing to do with the Python. It has to do with the state of the wider tool set and decisions that we made. And I frequently found that to be the case. I mean, there's a famous problem that you run into with Python with a load issue, which we can talk about later. But that really hasn't bitten us as badly as some more standard problems that are shared by the rest of the community for finite element methods, at least, not so much finite difference and finite volume methods.
Have you compared your code with any other similar codes about compare the runtimes? For example, like your code takes 100 seconds, the other code takes 20 seconds or 200 seconds.
That's one of those things that we do from time to time, but I don't have a good recent result. Because we've been focused on sort of refactoring and optimizing. When we did it earlier, let's see. I can point you to a paper on PETSI for Pi and MPI for Pi that does large-scale tests of the linear algebra portion and shows comparable performance there, that you're really not getting much of a hit for using Python in that way. But in terms of the full-blown code...
The reason I'm asking is, yes, PETSI and MPI for Pi, yes, those are still libraries that one is using. But when you are writing a full code, for example, you have a code, there will be a lot of other things, a lot of overhead. And yes, it is very easy and comfortable and convenient to write your whole flow solver, whatever that may be, in Python. There may be a large overhead involved. It could turn out that a person who has written the whole thing in C or Fortran gets the job done in 20 seconds, where your code takes 40 seconds. And then being the HPC community, that becomes a very big issue.
Well, yeah. So one thing that would be relevant here, it's not a comparison, but it is it's still quantitative, which is serious profiling of the code. And we've done a fair amount of that lately, and we're spending all of our time in PETSI at the C level. And so that's not as good as a comparison to a code that does exactly what we do, but it is a quantitative demonstration that the hit that whatever hit we're getting, it's not Python. It's algorithmic, and it's inherent in that particular system and PETSI. Aaron, did you have something?
The first question is, can you write an entire code in Python and have it be performant, right? Where all aspects of the code are in Python, and the answer is no, right? Python's interpreter on nested tight for loops is about 1,000 times slower than C or Fortran, and that's a completely unacceptable performance loss. Now, there are a number of tools within the Python community that mitigate this issue. The first is that Python natively wraps Fortran in C, and actually NumPy is about 70% C. And so Python, this is called an extension module in Python, and so all of this fast operations actually go out to either libraries or compiled or generated C or Fortran code. So what Phoenix does when it generates this fast code is it's actually calling out to another library that explicitly basically writes out C assembly routines for your finite element space, and then compiles those with optimization settings turned to maximum. So if you were interested in switching to Python or using Python, what you would do is you would actually wrap your existing kernels with Python, and then you would use Python at a high level, because there's this sort of 80-20 rule to high performance computing, where 80% of your code is occupying less than 1,000% of your time, and it can be written in anything, right? And so it's better for it to be high level and easy to maintain. And then for that 20% where the performance really matters, then you don't write that in Python. You have to use some other language, or you have to use some acceleration technique like Python or something else. I wanted to come back, though, to the performance comparison. There's another paper that I wrote or I was involved in. It's just the PyClaw paper, which is in SciAm Journal of Scientific Computing, where we explicitly compared a Python reimplementation of the Clawpack library. And in that case, we did directly compare the Fortran and the Python code. And one advantage, of course, was that Clawpack is a serial code and PyClaw is parallel. So just comparing the two codes just directly against each other, we did observe something like a 20 to 30% performance hit in going out to your wrappers, right? And that's for very lightweight wrappers. But as soon as sort of that overhead is on the order of milliseconds, or as soon as that's mitigated, as soon as you're not having tons of function calls in Python, the performance is the same, and that we've observed.
Yeah, just to repeat and to clarify, I'm not suggesting in any way, and neither has Aaron, that you go out and you rewrite everything that you're doing in Python or any type of language like that. That's not the approach we ever took or suggested, and I don't think you were asking that. The question of actually doing the head-to-head comparison, I get that too. I think it's very important that at the end of the day you say, look, I've got to solve that wave problem. I want to see your code versus that code that does the same thing, and how much longer does it take?
And I mean, being here, and being in the HPC community, you will always, and by you I don't mean you, but community will always face the question where, the person who has the machine will say, you have to show that your code is efficient, and you have to justify in some manner, and that was the reason behind my question.
Yeah. We thankfully have not had a lot of resistance on that, like people looking at our choice of programming languages and things like that. I will say another thing, that a lot of times when you get to that level, of course, you're not comparing apples and apples anymore. So the one comparison that we did do when we looked at what was actually happening is our Python code uses fairly sophisticated adaptive time stepping. And you can do that in Python. And you can do really nice stuff, because that's where sort of Python doing a lot of complicated decision making and things like that. So we did that relatively easily. Then the traditional C code, of course, doesn't have something that sophisticated. And this is, again, back to Aaron's example, a better algorithm wins almost every time. And so even though in that case our low level, our residual and assembly stuff was definitely slower, we were wasting a lot of memory and things like that, we took more optimal time steps in that one, So it's not again, that's not a fair comparison. But I think also just the general classic software engineering for HPC, write the code, you make your decisions, try to do a good job, but profile, and be scientific about the way that you optimize. Don't just get hung up on trying to write super fast code using, inline functions and templates and all this kind of stuff. Do profile it, and that's what we did. We did our prototype in Python, we profiled it, and we said, that's got to be rewritten in C, that's got to be rewritten in Fortran or whatever, and went from there. And that's why we know at the end of the day, we know we're not really spending most of our time in Python. But we still run into cases every now and then where we'll write something new, and suddenly we've introduced some Python code that really is hurting us. So you have to continually go back and look at your profiles. Okay.
Can I add
yes.
something to it? I won't take long, but I will say, certainly on a lot of platforms, like especially like the top few systems and like Mira, right? Even doing your full computation or even a decent fraction of it in Python, very few people do that. We do not. One thing that might be valuable to know is I don't think anybody in this space thinks that making everybody write Fortran and C all the time or C++ is the right solution. Right, is like the best possible thing we could do. But for a lot of reasons, right, that's what tends to work best. But it is a problem that, while it's not like we have millions and millions to throw at it, it's still a problem we know and we want to address over time. But it's going to take a long time, and people have been trying to think about it for even before this now. But this issue of productivity, not having to write in the lowest level language, is something we would like to see resolved, maybe in my lifetime. Maybe.
So moving on to one really important other unresolved problem is this problem of actually, once you've written your code and you've made all these decisions, how do you get your software out there to more people? These can be important collaborators, people that can help you extend and make your code better, or it can be your downstream users, which, that's being in the DoD, I'm kind of somewhere in between more pure research and really, having real customers out there that we need to hand them something that works. And you got to start thinking about this. The way that you're going to distribute your software is important. And I think, again, this actually leads back to the talk last night. How do we justify the expenses of these really expensive machines? Well, we have to justify that based on the science that we do. And I don't think we're going to be able to justify it based on the science that we in this room on the HPC systems do. It's going to have to be one step removed, scientists who are actually using HPC to actually get their work done. And so to solve this problem, you've got to deal with distribution or package management. And so in Python, it comes up it bites you really hard because we're making an effort to really use high quality packages that already do a piece of what we need to do. We don't write our own linear algebra. We use Numpy. We don't, we use PETSI. And so we end up building up a pretty long dependency chain to do what it is that we need to do. And now that just becomes a nightmare. You can have extremely long build times on supercomputers, and you have to deal with a bunch of different compilers. Almost our stack always requires a Fortran compiler, a C compiler, C++ compiler, and a Python interpreter. And getting those all playing nicely together is hard. And so we ended up working on this tool called Hashdist, which is sort of the initial group that worked on the development was Dag Sverre Seltjebatten at the University of Oslo, Andre Chertik, who's now at Los Alamos, and myself, started developing a prototype, and then Aaron and Andy Terrell and a number of other people kind of joined in. And the basic idea here was to come up with a new way to specify your whole stack and a new way to orchestrate the build of each package in those, okay? And so the things we didn't want to do was write a new build system. We're not trying to replace Cmake or Auto Tools or anything like that. We also didn't want to create a completely sort of vacuum sealed environment. That's certainly one approach to making your code portable, is to build every single thing that you need. But you really can't justify that on an HPC machine where you have a number of important libraries that need to come from the vendor, okay? Another thing is that you deal with on supercomputers is a lot of this stuff really has to happen in user space. The burden falls on you to build a lot of your stack, and so you can't always go to the sysadmins and say, I want you to build these 20 packages and put them somewhere for me. So it has to work. It can't only work for the sysadmin or the root user on a machine. Again, it's not, even though the problem arose out of a number of us who were doing scientific Python, it's not unique to Python in any way. So PETSI itself has to address this issue, and it does it in its own way within PETSI. So let me try to give a quick explanation as we wrap up, and I'll do that by means of an example. And apologies in advance, I could not get my fonts and stuff to work to get these examples a little bit more readable. But here's an example of a package definition. So in this case, say I need to build OpenBLAS because I don't have it on my system. Hashdist uses YAML, which is a text-based format that's supposed to be human readable. And what we would do here for OpenBLAS is first we would kind of use inheritance, and we'd say OpenBLAS, it's going to be built just like our general base packages, okay? So this is, you can think of that as inheriting from the base package, this extends statement. And then the next section says, okay, what is the source for OpenBLAS? And it gives a URL, and that could be a straight URL to a tarball, or it could be a Git repository, or it could be various other formats. And then we give it a key. And what that key is, the first part of it tells us what kind of format the source is in. The second part is a hash of that source, okay? So it's the checksum. If you're used to Git, you know that each Git commit has a commit ID, which is a cryptographic hash, and that's exactly what you would put there to grab a particular Git commit. In the case of a tar file, it's a checksum, which we have a tool. If you know what URL you want to use for your source, we can run a tool that will download that source and tell you what to put as the key. So that specifies your source, and it does it in a nice, secure way. If something changes at that URL and the key doesn't match anymore, you're going to get an error, and it's going to tell you that something bad has happened. Okay, and we've had this happen in a number of cases where, not in OpenBLAS, but in other models, v0.2.8 changed without an increment to the version number. Okay, and we caught that because of this. So anyway, that's nice that we've got a hash of our source that's coming in for just OpenBLAS, but then we also have some other stuff. We tell it what the build stages are. In this case, we're going to do make and install all at one time. We give it a prefix, and it has this funny artifact thing, which I'll talk a little bit more in a second. But sorry, I got a line continuation. This is basically just doing make, and then the next line is install. And then it gives it some more instructions to say, when this package is a build dependency for some other package, I want you to set these environment variables in the build environment of that downstream package that depends on that. So, any quick questions on that before I move on? This is, again, you can kind of think of this as a meta build script. This is not telling you how to build it. This is using make to do the building. This is doing the higher level thing of saying, what precisely is the source? How do I orchestrate that build? And what do I need to do to use this package? Here's an example of something that you only would need on an HPC system, right? This is that case of, this is actually our host MPI package. You don't want to build MPI on most HPC systems. In this case, you create a package so that the build system kind of thinks that it has an MPI package that it's building, but all it's doing is it's setting some variables that you need to use that package downstream, okay? And so this is kind of the pragmatic aspect of Hashdist. It violates some of our ideas about pure reproducibility, because in this case, somebody's got to set those environment variables, and you can potentially change it without detecting it, but we hope to improve that a little bit later. But this comes out of the need for, first and foremost, this build system has got to work well on HPC systems, and it's got to use vendor supplied stuff. So here's a stack specification, and this is the Proteus stack. And what you see is, first of all, it extends a basic stack called debian.yaml. So this is a Linux-based stack. And then it gives you a list of packages. And most of these are just simple, package name : Some of them have special parameterization. So for Cmake in this case, I'm going to tell it a particular package I want to use for Cmake. So use the host Cmake, use the host BLAS. When I get down to MPI, I don't want to use the system MPI because this is for my Linux machine. I tell it use mpitch, and then we've got an mpitch definition. Then we get down to PETC, which is a little bit more highly parameterized. In this case, we kind of have to balance between PETC's ability to deal with its own upstream dependencies and our ability to provide many of those. And so in this case, we tell PETC, I want you to build with our Parmetus, but then I want you to download SuperLU, SuperLU-Dist, and Hyper and build those in your own way. And then it gives you some other parameters. And so this is how we build up the stack that we need to run Proteus. The central feature is that we're going to generate out of a package a build artifact, okay? And this is a functional idea. You have inputs that produce a unique output, and we identify that unique output by building a hash of all of the inputs. So the source for the package and all of the hashes of the upstream packages that thing depends on. That gives us a unique identifier, and then we put that build artifact in a kind of database that is keyed on the hashes of the build artifacts. this has a lot of nice side effects. Number one, you can build many different configurations of the same package and they coexist on your system naturally, okay? If you change the options to your build script, that's going to change the hash. If you change the upstream dependencies, it will change the hash. Or if you change the source, it will change the hash. And so on my machine, I've probably, got, if I looked in a directory, I might have 20 different versions of Petsy that I pulled in at different times because I might have wanted to take a peek at the development version, or I might have wanted to change an optimization option. And these build artifacts are saved so that I can, once they're built, I can quickly switch between these existing artifacts. Number two, it's a proven approach. We didn't invent it. There's a project called Nix that implements this in the context of a Linux operating system and a package manager. The reason we didn't use Nix is because Nix implements this in a very pure way where it's fully in control of the entire environment, and we had to be pragmatic about dealing with the HP systems in this notion of host package or vendor supplied package. And again, this leads to some nice things, rollbacks and easy switching between multiple built versions and multiple built stacks. And it also leads to reproducibility of builds, which I don't have time to do justice to, but obviously it's been a very important part of this workshop, the notion of reproducibility. So getting started, there's a landing page that gives you some basic, real kind of quick one-liners about what Hashdist does, and that's at hashdist.github.io. And then Hashdist is also another example of a community code. So most of the funding came from my laboratory and from Simula Research Laboratory in Norway. But from the get-go, we said, anybody who can claim copyright, we're going to release this under a liberal open source license. And so for that reason, it doesn't exist in the ERDIC organization. It's got its own organization on GitHub, and the license is the 3-clause BSD license, which is a very liberal license. Basically, you can use it for whatever reason you want to. It's also got a growing developer community with people beginning to use it for their own reasons and coming back and contributing to the development of the core Hashdist tool itself, as well as all of those package definitions and things that you need for the system to be actually functional. And this doesn't have anything to do with the design. It has everything to do with just the positive aspects of community development. Some guy pops up on the list and says, hey, I want to build Julia on the Blue Gene queue using Hashdist, and then we start to work together and go to town. That unfortunately hasn't happened yet, but they have built Julia on other systems, and that would be something for me that I might want to do this fall, but now we've had somebody who's jumped on it and gone ahead. All right. I'm going to skip the IPython notebook. You've seen a demonstration of that because that's what my whole presentation has been done in. It's another tool that came out of the scientific Python community. It also is important for things like reproducibility and making your good science and HPC available to other people. I have a demonstration, if you're interested, where we use the parallel infrastructure underlying the IPython notebook to run an HPC system from a web-based notebook running on your laptop. So you go and you see me request 500 cores on an HPC system. It goes out and starts that job, spins up the engines, and then we run an analysis from the laptop, from the web. And that's it. Thank you for your time. Question?
So how does Hashdist compare to something like Cmake external projects?
It is kind of closely related to the Cmake super build functionality. Certainly has some of the same objectives there. I've used the super build just once or twice to build some stuff that we've been working on together with Kitware. I don't know the fine details of that. I will say that we are one of our contributors to Hashdist is a Cmake developer as well. And we've had a joint project with Kitware to build a lot of their tools within Hashdist. And so the core developers of Cmake have looked at Hashdist and kind of agree with a lot of the decisions that we've made, and they like the approach. That doesn't necessarily mean that the super builds are going to go away or anything like that, but hopefully we'll get very nice integration between the two things. And we've already got very nice integration between Cmake itself. Certainly many of the packages that are in Hashdist are Cmake packages, so it works very well at the Cmake stage. That's about it.